Hello and welcome to Empowered Learning. This video will be about polynomial basics, and in particular we will talk about the anatomy of a polynomial as well as some of its basic properties so that we know whenever we're looking at a function if we are actually looking at a polynomial or not. So the example that I have here, which is 5x cubed plus 4x squared minus 1/2 x plus 3, is an example of a polynomial. And so one of the ways that we can describe a polynomial is just by saying it is a sum of power functions. And so we need to first identify what a power function is so that we know what we're talking about. So if we have any function of this form here, where a is some constant and n is a fixed constant and x is a variable, then that is an example of a power function. We're very familiar with these if you've been doing mathematics for a little while, because functions such as y equals x, or y equals x squared, or y equals x cubed, all these are examples of power functions. Now, before I move on, I want to make sure that we make the clear distinction in between a power function and an exponential function. An exponential function is a function that looks like this: a raised to the x, where we could have some other constant in front of it here. And I'll go ahead and erase this and put that there. So let's say I'll write it like this. So a times b raised to the x. Now, the thing that's different here is that a is some constant. Let me write that again to make it a little bit more clear. So a is a constant, b is a fixed constant, meaning it's just going to be one number, and x is the variable. And so in relation to what I have here, if we said y is equal to 2 raised to the x, then that is an exponential function. And if we had y equals 3 raised to the x, that would be an exponential function. Also, we could say something like -5 times, let's say, 4 raised to the x. That would be an example of an exponential function as well. So to put it simply, if we had an exponential function, the exponent is a variable. If we have a power function, and the exponential is some fixed constant. So that's a quick way to be able to identify whether you're looking at a power function or an exponential function. So here we see that this example here shows us that we have a sum of power functions. And so as we read through this, we'll see exactly what that entails. And we'll also go through an example or exercise where we will try to figure out, are we looking at polynomials or not? So moving on here, in general, we have our polynomial written in this form, and you see this in most textbooks. And of course, when you first look at this, if you haven't seen anything like this before, it looks like gibberish, but really what we're trying to do is in a systematic way sort of let you know what every number is according to its placement in the polynomial. And so that's why here I say every a sub n minus 1, a sub n minus 2, so on and so forth, are coefficients. And that is to say, these are real numbers next to the variable x. And n here, which is the exponent that's here, is the largest exponent or the highest exponent on the variable x. So if we go back up and look at our example that we had here at the beginning, if you notice here, the degree of this polynomial is going to be 3, meaning the highest exponent is 3. And this 5 here would be considered the a sub 3 coefficient. this 4 is the a sub 2 coefficient. Negative 1/2 is considered the a sub 1 coefficient, and 3 is considered the a sub 0 coefficient. So 5 is the coefficient that is in the term for x cubed. 4 is the coefficient for the term that is with x squared, so on and so forth. So that's how we label this. And of course, you see how this goes in descending order here, where this is an understood 1, and here we have an understood x raised to the 0 there. And we know from our exponential rules that anything raised to the 0 other than 0 itself is just equal to 1, because this is a fancy way of saying x divided by x. Okay, so now that we know what all the a sub n's are and what the n's, the n minus 1s, the n minus 2s are, we can see that it's relatively simple. Okay, so let's go ahead and move on and talk more about the degree of a polynomial. So the degree of a polynomial n lets us know at most how many times the polynomial function can cross or touch, and I'm going to put that in parentheses here and I'll explain why later, the x-axis. So put another way, the degree tells you at most how many x-intercepts the polynomial function has. And so here when we say x-intercepts, we just mean the number, well, we mean the locations or location of where your function can cross or touch the x-axis, okay? Points on the x-axis where the graph crosses. Now, the reason why I say touch, or a more proper way to say that is tangent to, is because sometimes we do not have functions where they actually cross the x-axis. Sometimes they just kind of bounce off of it. And so a good example of that would be, if we look down here at other examples of polynomials, this polynomial right here. And of course, if I were to write this in a more simple form, this would just look like x plus 2 quantity squared. And that basically looks like the graph of x squared, which basically looks like a u. But the only thing that's different now is, since it has x plus 2, this graph is sort of shifted over to the left 2 units. So that's why it looks like this. Now, the main part that I want to focus on is, do you see how the graph touches the x-axis? Well, touches the x-axis, but then it goes back up. So that's what I mean by it touches. A more proper way to say that is tangent to the x-axis when it does this sort of this sort of action here. Now, I'm going to erase what I've just written here so that I can go over these examples here so that you can kind of understand what you're looking at. All right, so the important thing to know about polynomials, or to me the interesting thing, is that polynomials are sort of like the Play-Doh or the clay of mathematics, meaning that polynomial functions are functions that have this characteristic to where they can sort of mold to or model the shape of anything. And so, of course, mathematically, whenever we try to model things, we're basically trying to give a representation of whatever that is, but do it in a math fashion. In a lot of ways, a lot of times we try to do that graphically. So anything that has a linear relationship, a relationship that so it goes up and then it goes down, or it dips down and it comes back up, and we call that a parabolic type of motion, or parabolic graph. Those things can be modeled by a polynomial function. If we had, let's say for instance, we wanted to model how high a particular person is when they're on a roller coaster, that could also be modeled by a polynomial as well. So my point is that mathematically speaking, most of the functions that you have studied before you start getting to exponentials and logarithmic functions or whatnot, or trigonometric functions, if you've seen that kind of stuff before, most of the other functions that you've dealt with are pretty much a subset of polynomials. So here we see that we have a horizontal line. That is an example of a polynomial. It's a polynomial of degree 0 because if we look here, 2 can be written just as 2 times x raised to the 0. And since x raised to the 0 is equal to 1, then 2 times x raised to the 0 is 2 times 1, which is just 2. Of course, this is just a horizontal line. All lines, when they're horizontal or either have a positive or negative slope, have a degree of 1, okay? And of course, what that means, according to the definition we just said, a line that has a positive slope, a negative slope, or a 0 slope, like the horizontal line, will at most cross the x-axis 1 time, or touch the x-axis 1 time, okay? It could be, the only exception to that is, of course, the line y equals 0, which is actually what the x-axis is, and in that case is crossing an infinite number of times, okay? But except for that case, all lines that have a positive slope or negative slope will cross the x-axis 1 time, at most 1 time. Now, quadratic functions are functions that have a degree of 2. And so these look like your parabolas, or functions that look like a U or an upside down U, okay? And of course, you have polynomials of higher degree. This one, so this is the one I was saying kind of looks like a roller coaster. We could basically model the height of a person being on a roller coaster by using a polynomial if we wanted to. So for those of you that are familiar with drawing programs, you know that you have this feature called freeform. And so that's kind of like what I'm doing here. So here, mathematically speaking, I could take this, if I put this on an XY plane, and actually model this to some function that looks like the polynomial, like how I had in the beginning, if I wanted to do that, okay? So again, the whole point of this is just to let you know that lines, parabolas, quadratic functions, and other functions to where if you just draw the graph of it and you can do anything like this, that could be modeled by a polynomial, okay? Of course, we have our cubic function over here too that can be modeled by polynomial as well, because it is a polynomial. All right, so in looking at this, we know that we have a lot of functions that could be polynomials. So one of the things that we need to know is, how do you know when we're actually looking at a polynomial? Because we'll have some instances to where we have some functions that aren't polynomials, but you may think they are, okay? And so what we're going to do is look at some special properties that we know polynomials have to have, and we will be able to distinguish whether we're looking at a polynomial or not based upon these restrictions. And so my point is this: we're going to figure out if we're looking at a polynomial by deciphering what polynomials don't have. And if we see one of the things, or I should say better, what polynomials can't have. And if we see that our function has something that a polynomial can't have, then we know it's not a polynomial, or it won't be able to be modeled by one, okay? So we'll go ahead and move up here, and we'll see, how do you know a function is a polynomial? Well, there's 4 things that I try to identify. The first thing is we can have no fractional exponents or nth roots in any of the terms of our function. So in the example that I have here, this says the 5th root of x cubed, or x raised to 3/5. So here, this is the fractional exponent. This is this fractional power function exponent written in exponential form. And I say it like that because really x raised to the 3/5 is not a power function. It's more of a radical function. They look different, but to kind of give you an idea, of course, this is x raised to some number here. So you can kind of call it that. But the main thing is no fractional exponents, nothing in nth root form. Number two, there are no terms where x is in the denominator of some fraction or rational expression. So here if we had 1 divided by x is a great example of that. You can't have that. And so the reason for this case in particular is we know that one of the things that is true about a polynomial is that the domain of a polynomial, meaning the x values that we're allowed to plug into a polynomial, ends up equaling all real numbers. And so this is how we express that in interval notation. And if you're not familiar with interval notation, that is okay. I have a video titled Interval Notation, and you can watch that to kind of get an idea of how to write a range of values of x in interval notation, as well as knowing what that is graphically. So you'll know what I'm talking about here. Okay. All right, so we know no fractional exponents or nth roots in any of the terms of a polynomial. We know we can't have x in the denominator at any time for the function that we're looking at. We also cannot have negative exponents, okay? So here, for example, we have x raised to the -3. This is the same as 1 over x cubed. And we know that because there is an exponential rule that says anything, if we have anything raised to a negative power, it's the same as 1 over that same thing raised to a positive power. So here, 3 is just an extension of 2, but if we realize that we have a negative exponent, we don't have to go convert it to 1 over whatever that thing is raised to a positive exponent to realize that x is in the denominator. Okay. And so the last thing I have listed here is all the coefficients are real numbers. So if you had one of the numbers that's next to either, let's say, x cubed, x squared, x to the 4th, that is not a real number, then you're not dealing with a polynomial. For example, let's say if I had f of x is equal to 5x to the 4th minus pi x cubed square root of 3x squared. Let's say this is going to be plus square root of -5x plus pi squared. So let's say we're looking at this particular function. So here we see that 5 is a real number. We know that pi is a real number. It's an irrational number, but it's real. Square root of 3 is a real number, but it's irrational again. But square root of -5, there is no real number that exists for that. So because I have this number here, square root of -5, that would make f of x not to be a polynomial, okay? So keeping those 4 things in mind, along with the fact that for the domain of a polynomial, for the domain of a function, if the domain is not all real numbers, then we cannot make the assumption that it is a polynomial. Now, of course, there are other functions whose domain is all real numbers and they're not polynomials, but we know that for a polynomial, that's the kind of like the first thing. If the domain is not all real numbers, then all bets are off at that point, okay? And so again, when we say domain, just in case you don't remember what that means, it just means that whenever we plug in a value for x into our function, that is a real number, we get out a value that is also a real number. And so the 2 things that we look for here is we don't want a case where we plugged in a value for x and we have 0 in the denominator. And we also don't want a case to where if we're dealing with, let's say, square roots or fourth roots, we end up with a number that is negative under the radical, like what we see here. So if we're plugging in values for x and we end up with like square root of -2 or square root of -5, then we know that that x value is not in the domain of the function. Meaning for every x value that's real, you don't have a corresponding y value that's real to go with it. So you don't have that point on the graph. All right, so now what we'll do is go through the example that I told you I was, or the exercise that I told you I was going to present, so that we can look at a set of functions and determine whether we're looking at a polynomial or not. All right, so here I have a list of functions, and we want to determine whether these functions here are polynomials or not. So for this first one here, we see that 4/3 is the first exponent. Sorry, is the first coefficient, and it is a real number. That's a rational number. 3 is the degree of the polynomial. Here we have an understood -1. Of course, -1 is a real number, and of course 3 is a real number. So this follows the profile of a polynomial. We don't have any negative exponents. We don't have x in the denominator of any of the terms that we have there. We don't have any fractional exponents or nth roots. So this is indeed a polynomial. On the contrary, if we look at example B is not a polynomial strictly because of the fact that we have this square root of x term, which is an nth root. And just to remind you, anytime we do square root of x, if we translate that in its fractional exponent form, it looks like this. So the square root of x here is actually a term that is a radical term. And I can't plug in all values of x in here and get out an actual real number. So for instance, if I let x be -2, then there is no real number output for that. So if I plugged in -2 right here, I wouldn't be able to get a real number out. So we know that this is not a polynomial, and we know that because we have the square root of x there, okay? Or we can say, if you want to put that in words, we have an nth root of x in it. So for C, we know that this is not a polynomial because of this term here. We have x being in the denominator of this particular fractional or rational term here, okay? For D, we see that, of course, we have the square root of x again, so that messes everything up. So this is not going to be a polynomial as well. So scrolling down, we see we have f of x is equal to -5. And so this actually ends up being a polynomial because if you remember, polynomials are can be just a single number here. So for instance, I can write this as -5 times x raised to the 0. So the degree of this polynomial is 0, which means it doesn't necessarily have to cross or touch the x-axis at any time, okay? And you see how it has the profile of a raised to the 0 times x raised to the 0, which is just a raised to the 0, since x raised to the 0 is equal to 1, okay? And so for this last one here, notice that what is under the square root sign here is a polynomial, but this isn't necessarily a polynomial all on its own, okay? Now, if I was to rewrite this, it would kind of look like this. And for those of you that are familiar with this kind of mathematics here, I could just simplify this to absolute value of x plus 2. And since if I plugged in, let's say, -4 in for x here, I would see that this graph, if I graphed it, it would kind of look something like this. And so my point here is that I don't expect if you're watching this video, to know at this point, when you look at this, that the graph of this actually looks like that. And the reason why this is not a polynomial is because you have what's called a sharp corner right there. Okay. So absolute value functions look like these, and one of the things that polynomials can't have is sharp corners. The reason for that we study more so in calculus, but to make it short and sweet, we can't have sharp corners. And so here we get a situation where we don't have a polynomial, something that's nice and smooth. In math, we like to call it smooth and continuous. We don't have that. We have something that is smooth except for at one value here, x equals -2, where it kind of abruptly changes direction. So for that reason, that's why this particular function here is not a polynomial. And it's because we have square root of something. Okay. All right. So I know I went into detail here on this particular topic, but I wanted to try to expound upon it so that you all understand that whenever you're talking about a polynomial function, you actually know what it is that you're talking about and what you're looking at. I would encourage you to go watch my other videos that will be talking about, depending on what it is you're trying to learn, it may be adding, subtracting, and multiplying polynomials, or you may be in a higher level course where now you're having to sort of figure out, if I take a polynomial that is in factored form, how do I sketch a graph of that? And so I have videos for those things, and I hope that you'll check them out to aid you in your learning. Thank you so much for checking out this video, and I'll see you on the next one. Take care.